Okay, so it looks like it's 12:30. Whoever can join us can join us. And meanwhile, what I'll do is let me take over the screen in case you guys have questions. I can work them out for you. Okay, so Hanan, you said you had a question about moment generating function?
Yeah, I mean, if we could do a problem from each distribution.
Well, why don't you give me, let's just start. We'll take requests from people. So why don't you give me the page and problem number you want to talk about?
Okay, sounds good. The page is 146.
146, you said?
Yeah. And if we can do 14 and also 20.
All right, well, let's at 14 first, okay? So this is section 2.11.
Yeah.
2.11, number 14. So what's happening here? In number 14, you're being given that the moment generating function for some random variable is given by 1/81, 2e to the t plus 1 to the, is that fourth power?
Yeah.
Okay. Forget about phi of t, okay? That's not interesting because that's an optional thing. That's just a different kind of generating function. So let's talk more about this part. Do we recognize this moment generating function, by the way? Notice 81 is 3 to the fourth power, right? So I could bring this in and I would then have 2/3 e to the t plus 1/3 to the fourth power. You see that, Hanan?
Oh, okay, now I see it.
Do we recognize what kind of random variable this is? Well, if you look at the table that I've given you that I'll provide you for the exam, this random variable x is binomial. N is 4. That's n, right? And p is 2/3. So if I wanted the mean for this guy, I already know it's binomial. It's n times p, which is 4 times 2/3, which is 8/3. I know the variance is n times p times q, which will be 8/3 times 1/3, or 8/9. I don't really care about phi of t for this course. I gave it as an optional problem, but the important thing is to recognize a moment generating function. Okay, does that answer your question at least?
Yes, thank you.
Okay. Did you have another question here?
I guess if we do like one more like that, let's say.
Well, more important, what about a problem like number 4? That's an important problem as well. In number 4, you're given the probability mass function, or in here, this case, a distribution, 1, 2, 3, 4. And the corresponding probabilities are 0.2, 0.3, 0.4, and 0.1. And you're asked to find the moment generating function and use that to determine the mean and the variance. Well, remember, m of t is equal to e to the etx, which in this case, since it's discrete, it would be the sum of e to the tx of I times p of x of I over all possible I values. By the way, in the continuous case, remember, it's an integral. So this would just be, in this case, it would be e to the t times 1 times 0.2 plus e to the t times 2 times 0.3 plus e to the t times 3 times 0.4 plus e to the t times 4 times 0.1, or I just get m of t is 0.2 e to the t plus 0.3 e to the 2t plus 0.4 e to the 3t plus 0.1 e to the 4t.
Then you take the derivative and you
Then
equate
if I
it to
take the
0.
derivative,
Yep.
I get 0.2 e to the t. And remember, the derivative of e to the at, where a is a constant, is a e to the at. So this gives me about 0.6. Remember, 2 times 0.3 is 0.6. E to the 2t plus 1.2 e to the 3t plus 0.4 e to the 4t. And while I'm taking derivatives, let me get the second derivative, and then we'll get to work. This gives me 0.2 e to the t plus 1.2 e to the 2t plus 3.6 e to the 3t plus 1.6 e to the 4t. M prime evaluated at 0 will just be 0.2 plus 0.6 plus 1.2 plus 0.4. What does that give me? 1.6, 2.2. If I did that right, what was that? 2.4? So that's equal to e of x. M double prime at 0 is 0.2 plus 1.2 plus 3.6 plus 1.6. What does that give me? 5.2, 6.2, 3, 6.4, 6.4. And I just got what, 6.6? If I did that right, this is 1.4. Okay. And this is equal to e of x squared. So the variance would be 6.6 minus 2.4 squared. Whip out a calculator, and that gives you the answer. Okay. I'm taking questions. There are 10 of you here now. Anybody else have any other particular questions they'd like to talk about?
Yeah, I have more of a general question for the moment generating functions. I think at one point we did integration by parts in order to solve some of the problems.
Well, that was, Tatiana, that was when you're looking at a continuous random variable. For a continuous random variable, the moment generating function is defined to be, again, e to the tx, but that turns out to be just the integral, say from minus infinity to infinity. It's usually some finite range, though, of e to the tx times f of x dx.
Okay.
And in some cases, you may need to use integration by parts. I don't believe that's going to show up on the exam because I don't want to have to spend time testing integration, something people are supposed to know anyway.
Okay, good. So I'm trying to study for the exam, but I wanted to make sure, like, I know how to do it, but I can make a mistake. But also, I think the end result was we were given like generalized MGF functions for like binomial hypergeometric.
Yeah, the tables. In fact, if you,
Yeah.
I'm going to give you on the exam, if you look in the back of the book,
It's like 269 or something.
there's a table on page 272,
Oh,
and there's also a table on page 274. I'm
okay.
going to supply you with those two tables.
Wait, the table, we're using the Z table from the book?
Again, let me just find them again. I just lost them.
Okay.
Hold on. On page 274, there's a table that has all the properties of the binomial, the geometric, the Pascal, all the distributions that we discussed.
Okay, cool. All right, I just wanted to double check that.
And there's also the table for the normal distributions to compute the answers. And that's the same table that's on page 272. It's also in the sections as well, but they're conveniently located at the end of the book. I'm going to supply those.
Okay.
And when you guys upload your answers, please don't upload those tables. I don't need them.
Okay. So whoever wants to go next, that was my question for right now.
Okay. Next question, anybody?
Professor, I have a question.
Yes, Anya?
Can you help me with section 2.12, number 24?
.12.
Number 24. Actually, I have one more, which is 30.
Hold on, let me just find it, okay?
Okay.
How many times should a fair coin be tossed so that the probability, I understand why this bothers me. So the probability of obtaining between 30 and 50 heads is at least, okay, what is that, 0.96? Okay, that's a hard problem, and let me tell you why. Not that it's hard, you need a really good calculator to do it. So here's the problem. Clearly, this is a binomial problem. This is number, what is this again? Number 24. This is a binomial problem. The parameters are n, which we don't know, and p, it's a coin, it's a fair coin, it's 1/2. And we want to know how many times, so the probability of getting between 30 and 50 heads, where x is the number of heads. And we want this to be at least 0.96, okay? So let me just tell you that, well, this probability, it's the sum of the following, right? It's the sum of n, choose k, 1/2 to the k, 1/2 to the n minus k, as k goes from 30 to 50, and we want this to be greater than or equal to 0.96. And by the way, this is just 1/2 to the nth power. So I can rewrite this problem as the following: 1/2 to the n, summation k equal 30 to 50, and choose k. And this is greater than or equal to 0.96. So the question now is, and this is what's bothering you, Sang-Yun, how do you find n? So at this point in the course, the only way to do that is by trial and error and a really good calculator. A calculator like the TI-89, for example, which has a sum key. And what you could do is you would guess at a value for n and then plug it in. And the calculator can actually compute this sum. Okay? And then what you would do is, if the answer is too low, you increase n. If the answer is too high, you decrease n. And by trial and error, you could solve this problem.
Okay, so, okay, thank you.
Okay, I'm not done yet.
Oh, okay.
There's actually a better way. The trial and error here is messy. But I did it with my calculator. I have a TI-89. And I was able to do it, and that's how I gave you the answer. I don't remember what the answer is, but I got it. Now, what else you could do is you could use the central limit theorem. That is, you could write this as 29.5 less than or equal to x less than or equal to 50.5. You'll see this is also going to be a little trial by error, but it's easier. And you'll see what I mean by that as well. We know E is n times P, which is 1/2 n, right? And V is equal to n times P times Q, which is 1/4 n. So that means sigma squared is equal to n over 4. So you could rewrite this using the central limit theorem. x minus mu divided by the square root of n over 4 less than or equal to 50.5 minus n over 2 divided by the square root of n over 4. By the central limit theorem, this becomes phi of 29. Well, let me just, hold on, I skipped a step. So this becomes P of, let's call this number for a second A, okay? And I'll call this number B, which is equal to phi of A minus phi of B. And you want this to be greater than or equal to 0.96. So what I would do now is the following. Rather than do it the other way, I'd actually put in the numbers here. I'm sorry, this is phi of B minus phi of A. Right? Phi of B minus phi of A. So let me do this. Okay. And phi of B would be 50.5 minus n over 2. And now what I would do, I want this to be greater than or equal to 0.96. Now I would use trial and error again. I'd choose a value for n, okay? I'd guess, choose n. If the answer is too low, change n, choose a higher value for n. If it's too high, lower it until you get an answer that's greater than or equal to 0.96. So this was a much harder problem, Senor, okay?
Okay. Oh, thank you, Professor.
You're welcome. Other questions?
Can you help me with number 32 as well?
In that same group?
Yes. So 32 is related to 31, but I got 31, but I cannot get 32.
Okay. Let me just see. A fair coin is tossed. Determine the probability of, oh God. Okay, so now what it is, let me just give you a hint because I think it's fairly straightforward. It's very similar to a problem that I actually work out for you in the text. Look at example 10. Okay? Because it's really almost identical to example 10 in the text. And if there's still a problem, Sangyun, you let me know and I'll work it out for you and I'll send it to you.
Okay.
Sorry, I have another question. This is more general too. So the exam, is it following the syllabus? It's sections 212 to 34.
It will emphasize everything from the last exam through section 3.3. The central limit theorem is not through the normal distribution. The central limit theorem will not be on this exam.
Okay, that's kind of good. And then I mean, this isn't part of the exam, but for the central limit theorem that we just did right now, you added the 0.5s to the interval.
Continuity correction.
Okay, and that's called continuity correction. Okay.
Yes.
Just want to make sure I'm getting that right. Okay.
Okay, other questions anybody may have?
You can ask me anything.
I actually have one. So this combines a few concepts. It's 3.3 normal distribution number 12.
3.3, number 12. What is, okay, 3.3, number 12, you said?
Yeah, it's
Hold on,
Yeah,
let me find it.
and 13.
This is 3.3, number 12. Consider the probability that x minus mu, an absolute value, less than k sigma. And suppose x is normally distributed with mean mu and standard deviation sigma. Okay. Okay. We know from Chebyshev's inequality that this is at least 1 minus 1 over k squared, right?
Right.
However, if we use the central limit theorem on this, assuming, of course, n is large enough, this by the central limit theorem will give us the probability of the absolute value of z. Oh, I'm sorry, not the central limit theorem. We just standardize this to use the z tables. So this is actually equal to, since we're being told that x is normal, if we make a linear change of variable, we always get a normal less than k. So this is exactly equal to this, or equivalently, this is between minus k and k. And this is equal to, if you want to work it out, 2 phi of k minus 1. In fact, if you look at this is now a standardized normal distribution. Now let's suppose k is 1. Okay?
Uh-huh.
That means it lies within 1 standard deviation of the mean. And by the way, so when k is equal to 1, if you work this out, the answer turns out to be about 0.68.
Right. Okay.
Whereas when k is equal to 1, all Chebyshev's inequality tells you it's 1 minus 1 over k squared. Chebyshev's inequality will tell you, hey, it's greater than 0. When k equal 2, this is roughly what, 0.93 if I remember correctly? We plug in the value 2 and figure this out. And if k is equal to 2, Chebyshev's inequality, which is 1 minus 1 over k squared, would tell you this is 3/4, when it's actually 93%. When k is equal to 3, Chebyshev's inequality will tell you 8/9, when this is like 99%. And that's the whole point of the problem, is to show you if you actually know the distribution, Chebyshev's inequality doesn't really give you very good results. It gives you bounds, but they're not very accurate bounds. It gives you Chebyshev's inequality. So this is the normal distribution, what we get, the exact answer. Chebyshev tells you in this case it was 0. In this case it was what, 1/2? In this case it was 8/9.
Mm-hmm.
Okay, so that was the whole point of this problem.
Okay.
And you had another question, you said?
It was actually the one following that. So I guess it's kind of like a proof.
Which one is that? I'm sorry.
13.
Okay. This says, okay, it's telling you, suppose, what do I call it? Suppose x is normal with mu1 and sigma 1 squared, and y is normal with mu2 and sigma 2 squared, and x and y are independent. Before I go any further, let me remind you, for any normal distribution, say the normal distribution, suppose V is a normal distribution with mean m and standard deviation s squared. That means its moment generating function is e to the mt plus s, s squared over 2 t squared, I believe. If you go to the table, you can look that up. I believe that's correct. Okay, now we're asked about W, which is x plus y. Now we can find E of x easily, E of W. We know E of W will just turn out to be E of x plus E of y using the linearity property, which will turn out to be mu1 plus mu2. We also know that V of W, since they're independent, there are no correlation, there's no cross correlation term. I'm sorry, there's no covariance term. And this would turn out to be sigma 1 squared plus sigma 2 squared. But that doesn't tell us what W is, what kind of distribution W is. It doesn't prove that it's normal. So knowing its mean and variance doesn't tell you anything about what kind of random variable it is. However, we do know that since W is equal to X plus Y, and these are independent, the moment generating function for W is the product of the moment generating function for X with the moment generating function for Y. Well, this one is e to the mu 1t plus sigma 1 squared over 2t squared. And this one is e to the mu 2t plus sigma 2 squared over 2t squared. And using the properties of exponents, I can rewrite this as mu 1 plus mu 2t plus sigma 1 squared plus sigma 2 squared over 2t squared. Now, if I call this number m and this number here s squared, I see immediately that this is W is a normal distribution with mean m and standard deviation or variance s squared, where m is mu 1 plus mu 2 and s squared is sigma 1 squared plus sigma 2 squared. I got this above, but I was able to get this from the moment generating function because the moment generating function uniquely determines the random variable. Okay, Tatiana?
Yeah, that's pretty heavy stuff.
I don't think so. I think it's very straightforward once you realize the reproductive property of the moment generating function. That's a straightforward proof. You guys just aren't used to proofs.
Yeah.
And by the way,
Uh-huh.
if you wanted to, you could generalize this proof if x1 through x sub n. If each of these is normal with mean mu sub I and sigma sub I squared, then the sum of all of these W is normal. Its mean is the sum of all the means, and its variance is the sum of all the variances. So this immediately generalizes to any number of independent random variables.
Okay.
Now, you can prove the exact same theorem, by the way, and here's one you might want to try, Tatiana. Suppose X is binomial with parameters P1, I'll say P and, no, let's make it, they have to be the same. With parameters P and N1. And suppose Y is binomial with parameters P and N2. Then you could show that X plus Y is binomial with parameters P, N1 plus N2. You might want to try proving that exactly the same way. And then you could do the same thing. Instead of binomial, suppose X was Poisson with parameter lambda 1, and Y is Poisson with parameter lambda 2, and they're independent again. Then this will be Poisson with parameters lambda 1 plus lambda 2. You might want to try proving those. They're done exactly the same way using the moment generating function. Okay, other questions?
I have another question. This is just about the exam again. So what time are we starting tomorrow?
Probably Probably around 10:30. I'll start about 15 minutes earlier.
Okay, all right. And did you post the group or like the Zoom meeting for that yet? Or
Yeah, I posted a couple of minutes. I actually posted it and somehow it disappeared and I reposted it. It should be there. You can go to check Blackboard. You should see it there. Or you should also get an email.
okay, I'll check.
Okay, so let's see if I can do an easy question for you. Where is this? Okay, so where is this from? Suppose f of x is 2/7 for x, 2/7 x squared between 1 and 2 and 0 elsewhere. And y is, say, 4x minus 2. Find e of y. So let me show you two different methods for doing this problem. The first method, of course, is to, here's method 1. E of y, using the properties, is equal to e of 4x minus 2. And that's just equal to 4 times e of x minus 2. So the easy way of doing this problem is now just find e of x. Well, e of x is just equal to x f of x from minus infinity to infinity, which in this case becomes from 1 to 2 was it 2/7 x squared? So this becomes 2/7 1 to 2 of x cubed dx, or 2/7 x to the 4 over 4 from 1 to 2, which gives me 1 over 14 times 2 to the 4th is 16. 16 minus 1 is 15. If I didn't make a mistake just now, I got 15 over 14. And substituting, therefore, e of y is 4 times 15 over 14 minus 2, or 60 over 14 minus 2. And whatever that turns out to be, 60 minus 28 is what? 32? Well, hold on. Firstly, let's make life easy. This is the same thing as 30 over 7 minus 2. And this just gives me what, 16 over 7? So that's what I would think is the easy way of doing the problem. Now, let me show you, because the last time I gave this problem, I remember somebody did something else. Now, the other way of doing this problem is we could find another way of doing this problem. E of y is equal to just y times g of y dy, where we have the PDF, g of y is a PDF of y. Let me show you why this is the harder way of doing the problem. So we first have to find g of y. Notice from here, I get y plus 2 over 4 is equal to x. So dx over dy is equal to 1/4. And by the way, y, if x goes from 1 to 2, y will go between, when x is 1, y is equal to 2. And when x is 2, I get 8 minus 2, y is 6. So I could use a change of variable theorem. Okay, where's that? by the change of variable theorem, g of y is equal to f of x dx dy. I just found that the x dy is equal to how much? Is 1/4. And what do I have? Between 2 and 6. So this is going to be 2. I'm going to replace this by 6. And remember, x is equal to y plus 2 over 4. So that g of y becomes f of y plus 2 over 4 times 1/4 over this interval from 2 to 6. Remember, f of x was equal to, what was it? 2x squared over 7. So this becomes y plus 2 over 4. So this gives me 2 over, this gives me here. So this would give me, this gives me 14, 1 over 4, 1 over 14 times y plus 2 over 4 squared, or 16, or 1 over 14 times 16, y plus 2 squared. I want to show you why this is the bad way. And now if you plug this into the integral for e of y, I'll take out the constant 1 over 14 times 16. It's the integral from where? From 2 to 6. And then it's y times g of y, which is y plus 2 squared dy. Notice this is a messy integral to evaluate. You could do a change of variable here, or you can multiply this out and then multiply by y. The other method is better. Okay, just wanted to mention 2 ways of handling the problem and why using the properties of expected value sometimes works much better. Okay, other questions? Anyone?
I'm looking.
I should remark is, let's suppose I tell you f of x is exponential. Let me say it differently. Suppose I tell you x is exponential with mean 2. What's the probability that x is, what's the probability that x is between 1 and 3? Well, remember, for the exponential, the mean is 1 over the parameter, what do I call it, a, or alpha, I don't remember. So if I'm telling you this is equal to 2, that means a is 1/2. So f of x is equal to a e to the minus, a is a half, a e to the minus, 1/2 x for x greater or equal to 0, and 0 otherwise. And by the way, for the exponential function, it's useful to remember that f of x is equal to 1 minus e to the minus ax. That's a very useful result. Why is that useful? Because anytime you're figuring out a continuous probability, notice the answer to the problem that I want to find. This is just equal to f of 3 minus f of 1 using the CDF, right? The CDF is really very useful for continuous distribution. That means in this example, f of x is equal to 1 minus e to the minus 1/2 x. So f of 3 minus f of 1, which is the answer to this problem, is just 1 minus e to the minus 3/2 minus 1 minus e to the minus 1/2. And that just turns out to be e to the minus 1/2 minus e to the minus 3/2, which is a nice answer for an exam. You don't have to do the calculation, but if you whip out a calculator, this will give you the numerical answer. So in general, when working with continuous distributions, the CDF is usually pretty easy to work with. It makes life very easy. So that's an important observation. And you'll see in some of the problems that I worked out for you in section 3.1, I tend to use the CDF pretty frequently. Okay. Other questions? Anyone?
I think mine was similar. Actually, for like you work out the example, but I still didn't get it. For section 3.2, page 190, example number 6.
3.2, number 6.
Yeah, it's a long one. I mean, I hope we don't have something like this on the exam,
Well,
but
let's see what the problem is. 3.2, number 6.
so, oh, page 90. You actually work at, it's an
I'm sorry,
example,
what page is it on?
190.
No, 190 is in this, right in the center of the text. I'm
What
not
do you
sure which problem. Do you mean section 3.1 or 3.2?
No, I'm saying it's an example that you worked out. It's similar to that one.
I don't, okay, so number 6. Okay, so I gave you, no, I didn't do number 6. Number 6 involves mixed distributions.
And then a portion, oh, okay.
So I didn't do that one in class purposely. And I told you I'm not holding you responsible for mixed distributions.
Okay,
Okay?
yeah, all right.
Okay. Anybody else have any other questions? What about in 3.1, a typical problem like problem number 2 or for something like that? Am I in the right place? Like number 1, I did number 1. So number
Page
3.
182.
182, which one?
Let's do number 4.
This is on page 185, you mean?
Section 3.1,
Number 4.
exercise 4.
Got the one you wanted? Number 4 or number 3, which one?
Let's do 4.
Okay. So here's what we're given. We're given f of x. So this is number 4 on page 3.1, number 4. We're given f of x is equal to k times x, 0 less than x less than 1, a quarter between 1 and 2, 3 minus x over 4 between 2 and 3, and 0 elsewhere. Okay. Let me observe that this looks, I don't know what k is. But if I actually drew a picture, I know between 0 and 1, it's linear, right? Between 1 and 2, by the way, I don't know where this point is just yet. Between 1 and 2, it's a quarter. I don't know whether it's higher or lower. At 2, this would be 1/4. And at 3, this would be 0. Okay. And it's 0 everywhere else. So let's pretend it looks like this. I don't know whether there's a jump here or not. But here's what I do know. This is 1. The height is a quarter. So this area is a quarter, correct? This is 1. This height is a quarter. So the area of this region is 1/2 the base times the height, which is 1/8. Do I have that right? A quarter times 1 is, okay. So together, these two areas give me 3/8. So what must this area be?
One minus 3/8,
Which is 5/8.
which is 5/8.
And by the way, if this is the line kx, that means x is 1. This height is k. So 1/2 the base times the height is 5/8. So k is equal to what? 5/4?
Yes, thank you.
Notice I didn't have to do any integration here. I was just able to look at the region, which means, by the way, that this point is actually up, it's up here. So my picture's wrong. And now I think the rest is pretty easy, Kanan, yes?
Yes, thank you.
Let me just point out, if you correct the picture, what did I say, k was 5/4? So for example, if you want to find the probability, I'll just illustrate one example here, between 2 and 3. That's this area, correct? And that area is just 1/2 the base times the height. And I got an answer of 1/8 without doing any work. So sometimes you can be clever and get answers pretty quickly, or geometrically without having to do much work. Because remember, an integral represents an area under the curve. So when you have linear pieces, as long as they're linear, you can draw a picture and figure out the area. You have a problem, of course, when curves look something like this, and you actually have to use the integral to do a problem. Because you don't know what areas on the curves are unless you use the calculus. In this case, I was able to use simple geometry. Okay, anyone else have any other questions?
Can we do 14?
Number 14. Let me see what that is.
With the point that is chosen?
A point is chosen on a line of length. Let me call it L. Okay, L in this case is 10, but we'll just say the length of this is L. So I choose a point. Suppose this is the point I choose. And let me call this point, that position X, okay? Where X is a number between 0 and L. So the question is, what's the probability that the ratio of the shorter piece to the longer piece is, what is that, 2/3? So let's pretend this is the shorter piece and this is the longer piece. So the shorter piece has length x, right? And then the longer piece, let's just say little l for longer. The longer piece has length L minus X. And the question I asked is, what's the probability that the ratio of the shorter piece to the longer piece is less than 2/3? So here's the problem. Now we're assuming, of course, that a point chosen at random on this line is uniform. So this is a uniform distribution. So let's rewrite this. This is the probability that 3x is less than or equal to 2L minus 2x. And that's equal to the probability that 5x is less than or equal to 2L. And that's equal to the probability that x is less than or equal to 2L over 5. Well, that's just equal to, for uniform distribution, the probability that x is less than 2L over 5 is 2L over 5 divided by the total length, which is just an answer of 2/5. So it doesn't matter how long this piece is. In this vein, suppose I tell you that a train arrives anywhere between 5 and 5:30 p.m. It's really the same kind of idea. Determine the probability the train arrives between 5:10 and 5:22. Well, this is clearly, the arrival of the train is uniform. And we showed for uniform probability, this probability is just, the total interval is what, 30 minutes?
The mean is AB, the mean is A plus B divided by 2, right?
But I don't have to, the mean is the midpoint, but I didn't ask that. I'll come back to that in a second. But notice the time interval in question is length how long? 12 minutes, right? A 12-minute interval.
Yes.
So this would just be the probability that arrives in this 12-minute interval is the length of that interval divided by the whole interval. 3 goes what? 4, 6 rather. 6 goes 2/5. If I asked, Hanan, what is the expected arrival time of the train? Since this is uniform, that would just be the midpoint between 5 and 5:30, right? And what's the midpoint? 5:15 p.m. And if I ask, what's the variance? Let's do the variance in minutes. Well, the variance is the length of the interval, which is what? 30 minutes squared divided by 12, or 900 over 12 minutes squared. That's a unit, square minutes. So the standard deviation would be 30 over the square root of 12 minutes. And if you wanted to know the actual time, it'll be, well, this is just a variance. I don't know what this is. This is some number in minutes. Okay, Hanan?
Okay, thank you.
All right. Any other question? Going once? Okay, so again, I want to remind you guys, make sure you remember how to upload as a PDF. And when you do, please don't give me back the tables I provided you with. That's my gift to you. All right. If everybody leaves, Hanan, you wanted to speak to me about something privately or whatever?
Yeah, sure.
Okay, so
Like,
why don't everybody
office
else
hours.
leave? And I'll see you guys tomorrow. Hope you're all ready for your exam. If anybody has an emergency question along the way, send it to me. I'll try to answer it. I can't guarantee it. Okay?
Yeah, thanks, Professor.
Okay, everybody. Thank you. Hanan, stay on and we'll talk after everybody leaves.
Sounds good.
Okay. I guess while everyone's leaving, so I had mentioned that I wanted to drop the class, but even though I can't technically, that's not my intention. So I
Okay.
just want to express that. Okay.
Okay,
Thank
and
you.
that's fine. We can talk about that another time if you'd like to.
Okay. All right. That's it. Thank you.